What's up, guys? Here comes Unit 8. It's me and Earl
Yo!
Who's that guy?
Who is that?
Why is he in here?
I don't know.
Okay.
Let's play this song in that UFC game.
So, summation notation. The sigma is summation notation. I equals the imaginary number in this equation, and 4 equals the quantity of how many times the imaginary number is going to increase. So, 2 plus 6 plus 12 plus 20 is what we have to equal to find the correct summation notation. So, what we're going to do is going to use either one of these formulas, n squared plus n, or n parenthesis n plus 1, and distribute.
It should say I. That the n is supposed to represent the imaginary number.
There you go. My bad.
That's okay.
So then, you're going to pretty much
Plug in.
plug in numbers. You're going to go by 1, 2, 3, and 4. And what I did, I used this one here, n squared plus n, and you're going to pretty much plug in 1 with that, and 1 with that, and that comes to 2. Right here comes to the 6. This comes to 12, and that comes to 20. Add it together, you get 40. And
The only thing changing within each of these parentheses is how the imaginary number is increasing each time. 1, 2, 3, 4.
and then, I don't know how to explain that. That's what I got.
Oh, that's just the answer. It's just right here. That's the formula that we're gonna come up with since it already equals 20.
And there you go.
No, describe this one. So this one has
Go.
a common difference of 3, 7 to 10 to 13, all the way to 40. But we have to find out a way how you can get 3 all the way to 40. So you could just add 3 all the way, but most of the time that's not always going to work. So we had to.
And it'll also take way too much time.
We had to mess around, basically doing the same thing up here with the type of formula that's going to work. And pretty much we came up with
3i plus 4.
So again, I is just going to increase each time.
And then you're just going to pretty much plug in
And
numbers.
if you plug it in using PEMDAS, we had to use, since it was 3i, you're going to multiply first and then add 4 each time.
And
That's how got to 40.
12, like I said, equals the quantity amount of times the imaginary number is going to increase. So you're going to do this 12 times.
That's if it's asking for the sum of all the terms together.
There you
and
go.
obviously, you can't just stop it if you find a formula. You have to find the formula, go all the way through. Bada bing, 282.
282 is your final answer. Boom!
All right, so poopy. Keep going.
Poopy. I just took a poopy in your bathroom. You might feel another one coming.
I'm gonna need some Febreze.
Might want to with that sriracha sauce.
Garlic. We're gonna make this so uncomfortable.
Yeah, especially when you're taking forever.
We're talking about geometric sequence, arithmetic sequence, and a special little equation that you can use if you can't use either of them. Okay, put it on me.
Put what on you? Oh.
Okay, so arithmetic sequence, if you just look at the paper, it's basically just a pattern that goes by 4 each time. Here's the special little equation we have for it. A(n) equals a plus n minus 1 d. D is the common difference. N is the number of terms. A is the first term, and an is the first term times the number of terms. So it's the last term basically. So for an example, if you have 24, 4, 6, 1, 4, it's easy. Just follow PEMDAS just to see if they match each other. Now for arithmetic series, it's different. It's a whole sum problem. It's an addition problem of 4 plus 8 plus 12. In other words, it's not a pattern. But it still has a common difference of 4 each one. On this one, you're looking at sum, which is the sum of all the terms, the number of terms, and you're going to be using division, which is a plus all the terms, the last term, last term divided by 2. And you just do that basically the same way, the same principle of that, except you're just finding the sum. This one you're finding the last term through the pattern. Now, if you're at a problem that you have no idea how to do, but you think you'd use a sequence or a sequence problem, there is a special little thing that helps you called sum sequence. It's all the way back here. I could just flip the page. Sum of sequence. Now this is if you can't use geometric sequence or arithmetic sequence, whether it's a problem with a pattern or something like that. So the formula is n times n plus 1 times 2n plus 1 over 6. So if you just plug in your numbers for n, 15, 1, 2, 15 plus 1, you just follow PEMDAS again, and you should come out, let's see, yeah, 1240 right here. And if you just did it the weird way where you like added it all together or multiplied it all together, taking like the long hour-long wait, you would still get the same exact thing.
This is just an easier way of doing it.
Precisely. All right. Going over the pyramid at Sleeza.
Sounds interesting, right?
Yeah, honestly. It's a type of pyramid scheme that works in a lot of businesses. Sometimes it's considered illegal, it just depends. We're gonna start out with 3 people. We're gonna say A is the boss, and he has 2 recruits, and they both have to get 3 other recruits, and each person has to get 3 more recruits. So what it's asking is, stop it. We're not doing that.
Aaron, where the bar's at? Can't even see how I don't do that.
What it's asking for is how many recruits, how many times, how many rounds it would take for just 3 people to start off getting 300 million people. So we're going to use the arithmetic sequence to find the number of rounds. So we plug in 300 million as the sum of all the terms together, and we plug in 3, since it's 3 people, as R, since they're the common product. You have to divide 300,000 by 3 to even it out. Basically, just divide each other. We're finding n. That's the actual representation of the number of rounds. Afterwards, once we slim it down, we're gonna multiply 2 by both sides, so this cancels out, and we have negative 200,000 equals negative 3n. Pull some algebra tricks, and there we go. We got 17.4 rounds, and that's the pyramid of Sleeza, boys.
Yeah, dog.
Okay. Now we're going to be going over retirement investment funds. So let's say for 20 years I deposit $5,000.
Make sure it's clear.
And I have an increase of 5%. See that? So we would find 5% so far. If you go over 1 year, it's 250, and it's just going to increase by that number, 5% of that number each year. So after 3 years, I would have a 762 interest, and how I found that was I just pretty much added that for a full 20 years, and then I did it without the interest. If it was just 5,000 each year. Now, if we're going to find the total amount of money that we're going to have after the 20 years, we're going to have to look towards the geometric series, which is good. Excuse me. I'm sorry. Geometric series, finding the sum of all number of terms and the common product, which is 1.05, which is basically 5%. That's the ratio, yeah. So just plug it in, 5,000 going into the number, that's how much the deposit is, and we plug in 105 for R, and then N is going to be 20, the number of years. We go plug in all that, we're gonna have 5,000 times 33.065. Now, when you put this into your calculator, put it in like how it is. Don't change anything. Don't round anything until you get to the very bottom. Otherwise, you're gonna have a whole different answer. What I got was 165,333. 30. Excuse me. In the second part, I needed to find out how much I got in the last year. So if it was just my 19th year, I could have just done a cool little thing in my calculator where it says 5,000, enter, second answer, enter again, times 1.05 plus 5,000, and then enter again. And I keep doing that 20 times. I would have seen every single number I would have had for 20 years. And if I just looked at the 19th time I'd press enter, I would have had 152,695. But if you want to find it the right way, you literally could just do it the whole entire way, the same exact way, except you just change your exponent to 19. If you can see that. Yeah, just change your exponent to 19. That's all you gotta do. You'll get the same exact answer. Now, for recursive rule, this is what I came up with. an equals an minus 1 times 1.05 or 5% plus $5,000. Now, the reason why our account grows the most is because as you deposit money each year, and you keep it in there each in your savings as throughout 20 years, the interest is going to grow. It's going to grow bigger each year, basically. Yeah. So that's your retirement funds, and that's all of Unit 8. Thank you for watching, and have a splendid day.